Alright, so the first question on the guided notes is essentially what I asked for your pre-doc. What is our definition of parallelogram? Okay. And I gave you a couple counterexamples that would essentially prove it wrong. Okay. Okay, so our definition for parallel is both sets of opposite sides of a four-sided figure are parallel. So in other words, it's a four-sided figure whose opposite sides are parallel. Couple people who I think were pretty close on those definitions. They just needed to say that the set of opposite sides are parallel. Okay? Now, when we were talking about triangles, we didn't have to worry about opposite angles or opposite sides. Okay? When we're moving up in the world, we're moving up to quadrilaterals, we do have to worry about those. Okay? We have to define what we mean by opposite sides and opposite angles. So how might we define opposite sides in this case? Now this isn't just true for parallelograms, this will be true for all quadrilaterals. How do we define opposite sides? Thoughts? For opposite sides, they are the sides that do not share a vertex. Opposite sides do not share a vertex. Share a vertex. Okay? So in this case, AB and CD are opposite sides. An easy way to tell, I mean, I don't even have to say I don't even have to draw the figure for you to figure that out. If I said AB and CD, there's no vertex being shared there. But as soon as I say AB and BC, they share the vertex B in their own name. That's a good way to check. So opposite sides are defined as sides that do not share a vertex. Okay. Well then, how could we define, possibly, opposite angles? How could we define opposite angles? Similarly, it's a very similar definition. They don't share a side, okay? So opposite sides do not share vertex. Another way to think about it is they don't share an angle. Okay? They don't share an angle. You want to think of that way. Okay? And opposite angles do not share a side. So if we're looking at angle BCD and angle BAD, you notice it didn't have any overlap of the sides. But as soon as I say CBA and BAD, well, they just shared the side BA. So they would not be opposite angles. Does that make sense? Everybody with me? Okay. So I know we're kind of, we defined parallelogram before we defined what we meant by opposite angles, opposite sides, but I think we have an intuitive understanding of those. So now, did somebody in here have something to do with congruence? Said something like that you had something with congruence, right? Believe it or not, I think you were very, very close, okay, within your definition. We have a theorem that says if opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. I should double check that. I might have said the converse. Yeah, I did say the converse. If it's a parallelogram, then opposite sides are congruent. Parallelogram. If it's a parallelogram, if I say that A, B, C is a parallelogram, then the opposite sides are congruent. That is theorem 6.3. If A, B, C, D is a parallelogram, then opposite sides are congruent. Okay. Now I want to talk about consecutive angles. Consecutive angles. And we define what opposite angles would be, but how could we describe consecutive angles? Yeah, try.
Angles of a polygon that share a side.
Say again?
Angles of a polygon that share a side.
Angles of a polygon that share a side. Okay. Yeah. Yeah. Because this extends beyond four-side figures. Even if we're drawing our octagon, which we'll see how I do on this. Not necessarily regular. We're looking at this one right here. Then the consecutive sides for this one would be here, because it shares this side, but also here, because it shares that side. Okay. So consecutive angles share a side in a polygon. Okay. Specifically quadrilaterals, that's what we care about. That will extend to our next theorem. Okay. Theorem 6.4. Consecutive angles in a parallelogram. In a parallelogram, consecutive angles are supplementary. In a parallelogram, consecutive angles are supplementary. questions so far. So these are all theorems, so these are all ones we are able to prove. Okay? I'll go through a couple of proofs if we have time. So think about this one. Consecutive angles are supplementary. What would that make opposite angles? If consecutive angles in a parallelogram are supplementary, then what does that make opposite angles? Opposite angles in a parallelogram are congruent. That's the next theorem. That's 6.5. In a parallelogram, opposite angles are congruent. And finally, last one we want to look at here. We're going to look at the diagonals. Okay. The diagonal, I didn't put this on here, but you should probably write it down. Diagonal of a polygon is a segment connecting opposite vertices. Diagonal is the segment connecting opposite vertices. Again, that's another one that we didn't have to worry about with triangles. A lot of new doors open up as soon as we go up to four-sided figures. Parallelograms are our favorite. They're kind of like the isosceles triangles of quadrilaterals. Okay. The last theorem that I'm going to give you talks about the diagonals in a parallelogram. In a parallelogram, diagonals bisect each other. In a parallelogram, diagonals bisect each other. Not necessarily. Not necessarily. Okay? Sometimes they are, and if they are, we have a very special case. It only happens one time. That will be something we will learn, though. Question was, are they necessarily perpendicular? No, not necessarily in a parallelogram. I mean, you can even tell, just based on the drawing, I know it's a little rough, not the scale, but even though you can tell, those aren't going to be perpendicular. Okay? In this particular case. Good question. So they bisect each other. What does that mean? What does that mean that they bisect each other? I'm going to call this point here E. Somebody tell me what that would mean. Give me a congruency statement. If they bisect each other, if AD bisects BC, then what? What does that mean? Say again? Well, okay, so that's not bisecting. Let's just be clear on what bisecting means. We have a segment here and a segment here. Let's give it some names: X, Y, and WZ. In this case, does yx, does yx, the vertical one, bisect wz? Does it bisect those? No, it doesn't, okay? We need a special relation in bisection. Bisecting doesn't mean they intersect. Bisect means it cuts it into two congruent parts, okay? So possibly, I mean, it's really poorly drawn, if so. Possibly WZ bisects X, Y, but a better one to look at is this one right here, okay? Where you can see that AE and ED are about the same length. They're about the same length, okay? So we can say AE, if BC bisects AD, then AE is congruent to ED. Okay? And furthermore, since they bisect each other, that means that AD bisects BC, so BE is congruent to EC. Okay? Just make sure you understand what it means to bisect, okay? Another way to think about bisecting, I like this definition a little bit better than, it splits into two congruent parts. I just say it travels through the midpoint of a segment. Okay? A segment bisector is a line that goes through the midpoint of a segment. Okay? Make sense? Okay. I want to go through a couple of the proofs and then I'll assign you your homework. Okay? Which the homework will be due on Monday. Just for the homework assigned today will be due on Monday. And then the flipped classroom, be prepared to come in and work on that tomorrow. Okay? I know with the Carnegie days being flipped around, it's kind of out of the funk, but hopefully we can get back into it next week. Okay? Just in time for spring break. So the first theorem. Let's look at that one. Now I want you to kind of flip your page over and go through this proof, just so that you know how to walk through a parallelogram proof. Okay? Because I will ask you to prove parallelograms on the next quiz. All right. So first one says if we have parallelogram, which is iffy, okay? We have a parallelogram, call it A, B, C, D. Okay. We have a parallelogram, then what? If the figure is a parallelogram, then what? The theorem states.
Opposite sides are congruent.
And opposite sides are congruent. Okay, so given, I'll make this nice and big here, it would go something like this. Given that AB is parallel to CD, and AC is parallel to BD, prove that AB is congruent to CD, and AC is congruent to BD. That's your task. Okay? Let's say that's our task, is to prove that. Okay? Step one is, of course, our given. Let me give you a second to write this down. Make sure you're writing that down. What are we trying to prove? We're trying to prove that opposite sides are congruent. Opposite sides are congruent. So I gave them names, so it's a little bit easier to walk through. Okay. This is a good skill to pick up, is to be able to interpret the words and put it into math terms so that we can prove. Okay? I promise you, it looks kind of intimidating right now, but we have the ability to construct things. Okay? As soon as I put a construction on this, I think it should become a little easier. Okay? So first, we've got our given. AB is parallel to CD, and AC is parallel to BD. here. Step 2. Okay? Now, you don't have to, if you make a construction on the paper, unless it's a very specific construction, like it's a bisector as drawn, or something like that. You don't have to state it in your proof. Well, what I'm going to do is I'm going to draw a line right here. Draw the diagonal, BC. Draw the diagonal BC. Or you can do AD, it doesn't matter which one you do. Okay, you don't have to put that in your proof either. That's a straight edge construction. There's nothing you need to do for that. Okay? So because these guys are parallel, A, B, and C, D, the opposite sides are parallel, then a transversal cutting through them forms congruent alternate interior angles. Say A, B, C is congruent to D, C, D. Alternate interior angles. Okay, good stuff. Step 3 is that BC is congruent to itself. That's a reflexive property. Again, I hope that at least for the kids who have had me for 3/4 of a year, I hope I've trained you well enough so that when you see that you've been given parallel lines, you automatically think, okay, what set of angles are going to be congruent? Okay? Are there going to be corresponding angles that are congruent? Are we going to have alternate interior, alternate exterior? What set of angles are going to be congruent? Because that's the immediate follow-up to that. Okay? So that's why it's hard to see there's no transversal in this case, right? Or at least an obvious one. No obvious transversal. Okay. So there you go. Drawing your diagonal, you'll be able to see alternate interior angles. And then, of course, again, maybe not as nearly as obvious, but if you see two triangles here sharing a side, always put the reflexive property down. Always put the reflexive property. When you have two triangles that share a side, always put down that shared side as the reflexive property on here. Okay. So that's definitely going to help. Okay. Running low on time. So here's what's going to happen. We're essentially going to try to prove that those two triangles are congruent. Okay. We're going to prove that those two triangles are congruent. Once we show that the two triangles are congruent, then corresponding parts of congruent triangles are congruent. CPCTC. Once you've shown that, you've shown what you need to show. Okay, so I'll leave the rest of the proof up to you. Okay, let me just give you a couple homework problems before you go, since we've got a couple minutes. So this was, again, section 6.2 in your book. Go through, let's do page 363. Page 363, let's do problem number 3. I won't give you too much since it's the weekend and you have already a full classroom to do. Let's do number 13, that's a good one. It's got a few parts to it, so you just kind of have to identify what the steps for that proof is. Okay. 25 through 27. 5 so far. Let's do 29 and 30. 7. 38 through 40. That'll be it. Okay. Don't forget about the flipped classroom. This is due on Monday.